How do you get a DC motor to hold exactly the speed you want? One of the most popular approaches is PID control. In this video, you will learn how to design a PID controller using MATLAB and Simulink. We will start with the PID Tuner app for the quick results. Then we will build the complete PID structure step by step with the control system designer to understand why we need all three gains. For this video, here is our model from Simscape Electrical. The DC motor block models all the physics internally. Output speed is measured in RPM. The controller subsystem is currently empty. We will build it. We are going to control the speed of the DC motor against the RPM reference. Let's run the simulation. We can clearly observe oscillations and steady state error. To improve the response, we definitely need a controller. Let's add the PID controller block in the controller subsystem. The default gains may not work. We need tuned gains for our plant. To tune these gains, we will use the PID Tuner app. These two sliders let you adjust response time and transient behavior interactively. Accordingly, it updates the PID gains for the controller. Once we are satisfied with the performance, we can update the PID block. We got 3 tuned gains. Let's run the simulation. The response is well tuned now, fast tracking, minimal overshoot and zero steady state error. This controller works. But here is the real question. Why do we need all three? What does each one do? Let's understand with the Control System Designer app. For Control System Designer, we need the linearized plant. Let us mark our linearization input and output points. And with the linearized function, we will convert this model to a transfer function. There is our plant transfer function. It has 2 complex poles, which means it is an underdamped second order system. Let's open the Control System Designer app and set up the feedback architecture. After selecting the appropriate architecture, load our plant transfer function from the workspace. The Control System Designer app automatically plots the Bode plot, root locus plot, and the step response. We can observe here that the step response has oscillations and steady state error. It also has a very low phase margin of 3.83 degree. Before we get into the details, we will add our design requirements to the plot. The Control System Designer provides various tuning and plotting methods which can be addressed here. We will use the root locus and Bode plot editors for this purpose, which are already added to the panel. Let's start with the proportional controller. We will right click on the Bode plot and open the compensator. Currently it's just a gain. We can move the magnitude curve to change it or vice versa. That the step response and phase margin are improved, but still there is a steady state error. This loop gain is our proportional gain Kp. Let us store this proportional controller and use it later for comparison with other designs. Adding an integrator gives us PI control. It puts a pole at the origin. That's what drives the steady state error to 0. But watch what happens to the response. The trade-off is very clear. The response gets slower and the gain margin is dropped. The integrator added phase lag. We need something to add phase lead and speed things up. That's what a 0 does. This can be handled by introducing a real 0 and tuning the loop gain. We will place the 0 away from the origin so it doesn't cancel the integrator's effect. It improves the response but doesn't meet settling time requirement. 1 0 doesn't give us enough bandwidth to speed things up while keeping everything stable. Let's store it and try a different approach. Here, adding a second real 0 will complete the PID structure and would work here. But in practice, a pure derivative may amplify noise at higher frequencies. So we will use a filtered derivative, a real pole and a complex conjugate zeros. Let's delete this 0 and introduce a complex pair of zeros and a real pole. Now we can drag these zeros on the Bode plot to tune the response. Now that our system meets all the requirements, we can save this controller. Let's move forward and compare all 3 controller designs that we stored. This comparison gives the answer to our question. We need all 3 terms: P for stability, I for accuracy, D for speed and robustness. And those 3 gains PID Tuner found exactly what we just built with the control system designer. Now let's put this to work. I'll export this controller to the workspace. From here, you can either use it as a transfer function block or extract the gains for a standard PID controller block. Let's run the simulation. We can observe that the motor tracks the target RPM with fast settling, no overshoot, and zero steady state error compared to its original response. Before we wrap up, here are the key takeaways. PID Tuner gets you a well-tuned controller in seconds. If you need a quick, reliable result, this is your go-to tool. The linearized function gives you a linear plant model from a Simulink model ready for control design. No manual state space derivations needed. Control System Designer allows you to go deeper. You can build and reshape your controller interactively, watch the various controls plot, update in real time, and truly understand how your design choices affect performance. Thank you.